Hi, this is Professor Fernandez, and in this video we're going to talk about Module 2 in Lesson 10. So the topic is triple integrals over rectanguloid regions. First thing I want to do is talk about what a rectanguloid region is. So in the previous video, we referred to these rectangular regions over which we were integrating double integrals. And we talked a lot about how to slice up these rectangular regions to approximate a double integral of f of xy with a double Riemann sum. So remember that this is very quickly what we had written down as the approximation. We had the output value of, this is the value of the function at all of these specific points that we chose somewhere inside or on the boundary of these subrectangles. That was this f of x y star. And then we multiply that by the area of the base of these rectangular subregions, thereby producing this rectanguloid that approximated the area of the volume that we were trying to measure from the function, right? So remember that picture. This is a very quickly drawn picture just to remind you what we were doing in the previous video. So we're going to generalize all of that in this definition and in this video to functions of three variables. So the rectanguloid region I want you to think of is kind of like the 3D version of a rectangle. So think of the 3D version of a rectangle as if it were a box, or later on we'll think of this as a loaf of bread. So we can have a very tall box that's not very deep. We can have a very short box that is also not very deep. And we can have boxes of all sizes, a very, very deep box. Here is an example. Here and going forward, I am going to try to stick to the standard notation that will help us figure out what we're doing and what space we're doing it in. So we will stick to R for using rectangular regions for double integrals, and I will try to stick as best I can to B for using the box notation for these rectangular regions in 3 dimensions that are now going to be associated with triple integrals. Okay, so that's just a quick little reminder of where we were in the previous video and how that leads up to what we're doing now. So back to the definition. Suppose B is a rectangular region in the xy plane, looks xyz plane, xyz axes, looks something like one of these boxes, basically. And suppose we now partition it into subrectanguloids. So this is where I mentioned earlier we'd want to think of it almost like a loaf of bread. So here is my box. How do I partition it? Well, I can slice it this way, right? And I've now created 3 different rectanguloids. I can also slice all of them down the middle this way, and I've created a bunch of other subrectanguloids. So just like we partitioned rectangles in the previous video, we can partition these rectanguloids. And we are going to get an M by R grid of subrectanguloids. And again, we denote by norm of P the maximum of the lengths, widths, and now heights of all the subrectanguloids in the partition. And then each one of them has a certain volume. Before, each one of these little rectangles in the previous video had a certain area. So now, instead of an area, we're looking at a certain volume of all of these little rectanguloids. And we're calling that delta V sub ijk for each one of the subrectanguloids. And within each one of these subrectanguloids, then we're going to do something very similar to what we did over here, which is we are going to pick those points inside these subregions and then substitute them into the function. Oop, let me go back there. I almost lost it. So, this is now a point in 3 space. So I can pick something inside here. I can pick it on the boundary. I can move around. I have a lot more space to move around to choose my special points x, y, z stars. And then finally we do what we had done before. So to run through that process. So we pick a point x star, y star, and z star. And this is in the ijk sub-rectanguloid. So imagine over here, for example, that's that one of this entire rectangular. And then we substitute that into the function that we are given. that we're interested in calculating the triple integral for, producing a, in this case, w value, not a z value, because this is a function of z, producing output. And then we multiply that output by the volume of that little subrectanguloid. So I'm just going to duplicate this, save some time, and maybe put it over here. So we multiply that output by the volume of this subrectanguloid. And then we add all of those different quantities across all of the subrectanguloids. And that produces, in this case, a triple Riemann sum. So I'm just going to move this over and write out that triple Riemann sum. So I then will have a sum over I, 1 to n, sum over j, 1 to m, as before, and then now I have a sum over k from 1 to r. So this then is an approximation of, that's what's over here, an approximation of the triple integral we are trying to calculate. And then, as before, when we take the limit as the maximum of the lengths, widths, and heights of all subrectanguloids in the partition goes to 0, we're kind of like doing what we did in the previous video. We're shoving or partitioning our box into tinier and tinier and tinier sub-boxes. And then the triple Riemann sum approximation becomes an even better and closer approximation to the actual integral. And in fact, provided the limit exists, we define, this is the point of this definition, we define that triple integral to be that limit of that Riemann sum. Okay, and then we say f is integrable over b if that's true. So, and again, last thing to point out here before we do an example, as in single variable calculus and as we did in the previous video, we can use this triple Riemann sum over here to approximate the triple integral above. I won't do an example there because it's much the same as what we did in the previous lesson, but just to know. I'll follow in the vein of what I had mentioned in the previous video. Once we've done Riemann sums once and talked about it, we kind of don't want to do it again. We want to actually evaluate the triple integrals or double integrals, not just approximate them. So back to then the question of how do we evaluate triple integrals exactly. And then here's Fubini's theorem again. I mentioned this would reoccur several times. Suppose a function is continuous on this rectanguloid. So first thing to notice that's kind of tacitly being conveyed here is notice that, as usual with the convention we talked about in the previous video, this is the x range, a to b, this is the y range, and now there's another one. So this is now the z range. So this is x, y, and z information. And so we are realizing that f is a 3-variable function in this theorem. Great, so then what do we know once we assume all this? Basically continuity on a domain of this form, on a box domain. Then Fubini's theorem tells us that the triple integral of f over this box region is really just this iterated integral. So it's the same thing we were doing, in the previous lesson, excuse me, previous video. We did not have a z as an input because it was a 2-variable function. And so we didn't have dz, and so we didn't have this last integral. So in the previous video, we just had this, this, and this. What we've added here is literally add the z and then integrate with respect to it. And that gets you to the triple integral. So, you might feel a bit strange that you perhaps might be thinking we could do this again for a quadruple integral or, 37 integrals. And that's true. There is not really, past double integrals. There's not really any additional magic that happens in higher dimensions functions of more than 3 variables, for example. This is really a bit more surprising in this case, though, because Fubini's theorem tells us that the value of this triple integral is the same regardless of the order of integration. So in the double integral case, we only had 2 choices, a dx dy integral, double integral, or a dy dx, double integral. Here we have many more choices than 2. And as you increase the number of variables, you'll have even more choices. But you will always get a similar Fubini's theorem, hence why I keep saying again. As long as the function is continuous, then the triple integral, or however many integrals makes sense for the number of variables the function has, will be calculable using any order for integration you want. Now, I should mention we're still talking about nice domains, right? We're still talking about rectanguloids in this case, very rectangle-ish domains. So that has something to do with why all these properties are working out so nicely. In the next lesson, we will generalize to discussions of more of less nice domains. Okay, so let's work on this example. And this one is intended to get us practicing with Fubini's theorem up here, and specifically with the iterated integral that I have to do 3 integrations for. So I'm given this box domain. I'm just going to try very quickly to visualize this. So we are having x go from 0 to 1, and then y is going from -1 to 2, and then z is going from 0 to 3. Okay, so if I visualize the x extent of this domain, it is from -1 to 2 in y and 0 to 1 in x. So that's as far down as it goes. And then I kind of go up to z equals 3, and I visualize the top portion of it. So this is my box domain, and it includes everything in there, so not just the boundary. So that is the region that I'm going to be integrating this particular function over. So let's talk about what we get. So Fubini's theorem says that the integral of this function with respect to the dv volume element, and again the convention there is unless you are told the order, you assume dx, dy, dz, and you put these as your x, y, and z bounds. So x is going to go from 0 to 1, and then let's see, y goes from -1 to 2, and then z goes from 0 to 3. Okay, great. So now let's go ahead and integrate this. And we'll see in a minute that this will reduce to a double integral first, and then to a single integral. So again, we are doing multiple integration by just integrating out the variables as we go each time. So the antiderivative with respect to x is the first one we're doing. So we're treating y and z as constants. This might as well be a product of 2 and 4. So we might as well be integrating like 5x. So basically the y and the z squared stay, and they go along for the ride as multiplicative constants. So my antiderivative here is x squared over 2 times yz squared. And then I substitute in from my fundamental theorem step the 0 and the 1. When I subtract the 0, because I'm subtracting 0 squared and multiplying stuff, I'm going to get a 0. So I won't write that part. And if I just substitute the 1 in for x over here, then I get 1 squared over 2, so that's 1/2. So that leaves me with just yz squared over 2, dy dz. Great. Okay, and then now I'm going to go off, and I am going to calculate the integral of this with respect to y. So now z squared over 2 is effectively a constant, because I'm only integrating with respect to y. And I get a y squared over 2 times that constant for our purposes here. Oh, and I don't need the integration sign. So I'm going to now do the fundamental theorem step from -1 to 2. And this is now dz. That's going to be left over. And then here I do have to kind of think a little bit about what results. So when y is 2, I get 2 squared 4 over 2. That's 2. And then times z squared over 2, so I just get z squared. And then minus, so I now put in -1 here for y squared. And I get positive 1 over 2 times z squared over 2, so I get z squared over 4 dz. And then I can simplify this to 3z squared over 4 dz. And there it is. So to recap a little bit, I up here was able to reduce the triple integral to a double integral. And then now here I am down here, reducing it even further to a single integral. And then I just do this integral like I would normally. Here I am again, suggesting that perhaps the properties that we know and love of integration carry over in the multivariable context? They do, so we'll see that in the next lesson, in the next module. So integrating here for z squared, I get z cubed over 3 from 0 to 3. These 3's cancel out nicely, and I get 1/4 times 3 cubed. So that's 27 over 4. Okay, so as we had mentioned before, it is a interesting thought to think about. What does that number mean? And unlike was the case in the double integral context, where the number we got was the net signed volume under the graph of f of x comma y, and between that graph and the xy plane. In this case, that's not the interpretation that we would think here. Because again, if we go back a little bit to the Riemann sum approach, let's think about what we were doing initially. We were taking something that was already a volume and multiplying it by the output value of the function. So we're definitely not calculating volumes here. If we go back to our box idea, the units of this are already something like, length cubed, meters cubed, feet cubed, or inches cubed, centimeters cubed, whatever unit you want to use. And then this also has some other units of length. So the output that I'm getting has units of length to the 4th. So it's not a volume that we're calculating. Although in very special cases, you can use triple integrals to calculate a volume. We'll talk a little bit about that in Module 3 in the next video. But so again, this is something that happens in this particular course. You may reach a point where the math has become abstract enough that it's hard to visualize. Certainly this is true if we want to try to visualize the graph of a function of 3 variables. Very difficult because we need 3 axes just to give you the points x, y, z, and one more to give you the output. So the graph of this lives in 4-dimensional space, which is very hard to visualize, if not impossible for most of us. Similar idea here. So we can calculate triple integrals, and they even have very useful applications, some of which we will explore throughout the course. However, that doesn't mean that every single value we calculate can be visualized or can be related in some concrete way to something we experience in the real world. All that being said, we have done our first example of calculating a triple integral, and really going forward, for these box regions, the only thing that will change is the bounds and the function. And again, as I mentioned in the earlier video for a previous lesson, you might have integrals that are left over, which you do need some advanced integration techniques to do. Perhaps partial fractions, trig substitution, for example, or maybe just good old use substitution. So there are single variable calculus things that you might have to remember in terms of integration. Great, so the next module talks about properties of double and triple integrals, and that is for the next video. So I'm going to stop here and do a very quick recap. Going back again to this definition, just clear things up here. This is the generalization of what we did for the double integrals in the previous video. And the only thing that would change if you wanted to apply this in context to help you approximate the triple integral of a function of 3 variables is that you have now an extra thing to worry about. You have a z value and you have a volume. Other than that, it's exactly the same process that we saw in the first example in the previous module. So the limit here has the same idea behind it, that you want to take the sub-rectanguloids that are generated by partitioning up your box region, and you want to make those even finer partitions, make them even smaller. And when you do that, as you do it over and over and over, your triple Riemann sum in this case, becomes a better and better approximation of something. It looks like it's tending to some value, and we define, when the limit exists, that limiting value to be the triple integral. And then last thing I'll mention, the Fubini's theorem recurs here. So if your function is continuous on the rectanguloid domain, then you can actually evaluate the triple integral, not just approximate it, by integrating 3 times. And last point to reiterate, integrating once in whichever variable you decide to do first reduces your triple integral to a double integral. So then we're back to the previous module's work. And then integrating one more time reduces your work to a single variable integral. So everything that you know how to do in single variable integrals you can use now to help you do triple integrals. Great, so I'll see you then in the next video.